Hi everyone, welcome back. Last time we saw how to set up the different components of the routing agent, and today we're going to see something very interesting, which are behavior trees. In particular, we are going to see how to use behavior trees to model the artificial intelligence, the brain of our agent. Turns out that behavior trees are a mathematical model that is very similar to state machines and represent how an agent, how a system should execute some tasks with some logic. But you know what? Let's go ahead and create our behavior tree here. So right click, AI, behavior tree. And we also create the so-called blackboard. So behavior trees and blackboards, they go together. And let's open it up and see how they work. So this is a behavior tree. Behavior tree is a tree where there is always a root node up here, and it executes a set of tasks that we're going to create now. See, right click and we have some tasks, some decorators, composites, and so on. Right now, what happens is that a behavior tree runs top down, left to right. In a second, we're going to add some tasks. So I'm going to show you. Here, what happens is that a behavior tree does the execution top down, left to right, starting from the root, with a certain frequency, and every time it does an execution, that is said to be ticking. So it's gonna tick once, it does execution, then tick twice, and execute, and so on. Right. So let's start without talking too much to see how a behavior tree works. So let's start with a simple thing, like being large. Well, let's put a task. A task, what is a task? A task is a leaf node, something that doesn't have any children. So let's say, for example, log. All right, this task, so we connect these two things. This task here, what it does is to log something on our console here, right? For debugging purposes. So this is a log, okay? Now, you see that I have a run button here. Why do we have it here? Well, with this run button here, we can simulate the execution of the behavior tree in the behavior tree designer. This is the designer, without actually simulating the entire system. Remember, we clicked on this run to simulate the entire system when we had an agent here in the decision network. Now, we just want to simulate the behavior tree. So let's go ahead and run this behavior tree. Very simple. This is a log. Here, just printed this, right? This is not much fun. Now we can do something a little bit more interesting. So we can add composite nodes. What is a composite? A composite is a node that has children, right? So we have a selector and sequence. Let's go with the sequence. A sequence node executes like this. Here are some description. A sequence node executes all children from left to right in sequence and returns when one of the children return fail. So this is the other piece of information that we need. When a node, a task here, is ticked, again, the execution is done in ticks, right? When the node is ticked, meaning that it's running, a node can return three different states. One is fail, one is success, and one is in progress, right? So let's go ahead and see how it works. So log, all right. Then we have another log. Very good. And this we say log A. All right. And then here we say log B. Very good. So let's see what happens now. We start taking the tree, top down, left to right. It goes here, running the sequence node is going to run the children left to right. So it's going to run first this and then this one here. And is going to return when at the first child that returns fail. Now, these children here are all log nodes, meaning that they're going to print something on the console and they're going to always return success, right? Return success. So no one is going to fail here. So basically what they're going to see is going to run the root, sequence, left log, right log, return success, nothing to run, done. So let's try to simulate. Perfect, log A, log B, right? So you see that now we run this, which was log A, and then we run log B. Now, let's say something interesting. We said top down, left to right. What happens if I switch this with this? So I switch this, all right? So now I basically switch these two blocks. This is B, this is A. Let's run it again and see what happens. Log B, log A. See, now, since we switch these two things, this run top down, left to right, and we run basically this first, which is log B, and this is log A. So now by simply switching the nodes here, the leaf node, we basically switch the execution. Very good. So let's see now what a blackboard is. So a blackboard that is, as we said before, is working with behavior trees. A blackboard is used as a shared memory to communicate information between nodes, right? So for example, let's say that a certain node here wants to talk to a certain node up here. How do we do that? How do we passage information? Well, we use a blackboard. A blackboard is basically a collection of values and variables, right? So let's open up our blackboard, all right? And let's say that we have, we can add some keys to the blackboard. And let's say my key is like my key, right? We say that the value is an integer. Very good, add key. So we have the key, my key, the value is 0, is an integer. And now we are going to, let's close this, we don't need it. We're going to set up this blackboard on this behavior tree. So click on the root, and we select the blackboard that we just created, right? And you see that indeed we have my key type integer. So what do we do with this? Well, for example, we can use a task where we have, we can create a random value, right? So let's do this. Let's create a random value. Random value block is a task block, so it's a leaf that basically puts into a selected key a random value. So let's actually do this. Let's delete these blocks here, and let's a sequence. So left to right. Let's set a random value here. All right, and we say this is my key from 0 to, let's say, 100. Okay, it's gonna set the value as an integer to my key. Very good. And then what we can do, we can print the value that we set, right? So we use a log value, leaf, connect this to this guy here. And what do we want to log? This, so you see the difference. We have a log and a log value. Log value is going to print the value of a variable inside the blackboard. So log value is going to print the value of my key. And why my key? Because it's the only key that we have in the blackboard, right? Very good. And we should see basically execution, top down, left to right, random value. We should see a value that is changing here. And let's run it. 1, 48, 55. 5. See, random value. So this is basically executing top down, left to right. This is setting a value until 5. And indeed, if we open up now the blackboard that we had before, you see that now the value is 5 here. It changed, right? Because this execution went on to change the value on our blackboard. Very good. You see that I'm clicking here multiple times to make it happen, to run it multiple times, but we could also avoid clicking here multiple times and just simply use a decorator block, a loop that is basically, it allows us to loop a certain subtree, right? The execution of subtree for a certain number of times. And this is a decorator. Decorator has one parent and one child, right? And it's going to loop whatever it is in the child. Very good. But instead of looking at that, let's look at something a little bit interesting. How do we do now? How do we do an if-then-else condition, for example, right? Let's say that we are modeling and then I'll show you how you use this kind of logic here, this kind of tree, to model the routing agent. So let's say that we want to add an if condition, if-then-else statement, where if our routing system, receive a certain trigger, then it executes an optimization procedure, something like that, right? So if you see, we cannot simply add, we don't have an if-then-else block here, right? we don't have something like that. The if condition is done a little bit differently here. So let's say that we do this. We add now a selector block, right? So composite selector. Selector is a little bit the counterpart of the sequence. So sequence run each child from left to right, and it returns the first one that returns fail, right? So this is going to set a variable like it always returns success. This is just printing, so it returns success. But there are blocks that can return fail. For example, in optimization, if the optimization goes wrong, right, we have actually here we have an optimized component. If that it returns like an error or something, that the block is going to return fail and it returns fail to the parent, right? So sequence runs left to right and returns the first fail. The selector instead does a little bit different. It runs every child left to right, but it returns at the first time it returns success, right? So this returns at the first failure, this returns at the first success. So it's basically a fallback mechanism, right? Try this down here, then if it fails, goes to the next one, and so on. So let's do a selector, and let's say now, let's create another sequence, right? Something like this. And now, what do we do here? Well, here now we do our if condition. So let's look at this. Tell you what, we can create a value comparison. Very good. This is another task node, so leaf value comparison, and then we say we can log value. Okay, something like this. So now let's see what happens here. And what do we compare actually? Let's compare less than the first value. Let's say my key, right? And the value here. Let's say we compare with 20, right? Very good. So let's see what happens here. When this guy here, the root, is gonna start ticking the tree, it's gonna start running the tree. It's gonna go here, sequence. It's gonna run left to right until the first failure. So it's gonna run first this one here. This is going to set up a random number into my key, as we said, right? This is gonna log the value, and it's gonna run the selector. The selector runs left to right and returns at the first success. So I start running this guy. This is a sequence, so left to right, start doing this. Value comparison, well, this is basically comparing what? It's comparing my key with the less than 20. So if this is true, if my key at this point in time here will have a value less than 20, then return success and it's going to run the next one, log. Otherwise, it's going to return failure. So return failure, sequence return at the first failure, return failure, and nothing else to do, right? Now let's add a little bit more things happening here to just complicate a little bit more, right? Let's add another sequence. And then let's see, replicate this thing here and say value comparison, right? Go like this, value comparison, and then we say this time we say greater than, and we say my key is greater than 70, right? And we set it. We add a log, all right? And we forgot actually to set up here. So we said that this is less than 20, all right? So we say random less than 20, okay? And this we said is greater than 70, right? So here we are gonna log value greater than 70. Very good. Let's clear this. So I'm gonna go here. If it's less than 20, then log, and then return success. So this is returning success. Selector, it doesn't need to go to fall back to over here. So fall over here. So return success, done. Otherwise, if it is like greater than 20, goes here, return fail. Oh, try the next one. Gonna go here, try to compare. Is it greater than 70? If yes, log. Otherwise, return false, nothing else to do. So let's run this thing. 68, and we see that now what we got, we didn't print anything. And we didn't print anything. Why? Well, because 68 is indeed is greater than 20, and it's also less than 70. So you see that this return fail, and we didn't print anything. So let's print something actually at the end, just to see that we are done here. Computing like this. So here I'm done comparing, right? So what is going to happen is going to run these things, set the value, go here. If it is less, print less. If it is otherwise, fall back here. Print if it is greater than 70, print here. Otherwise, go back, and then finally run this guy here, right? So let's see what happens here. Clear. 61. Nothing happens, and doesn't even print this one. Why? Because this is failed, this return failed, sequence return failed, so this doesn't work. So what can we do here? We could technically, to print this, always return success. So, oh, let's do this. Let's add a node that always returns success in any case. So let's do it here. Here. So let's say this return false. This is return false, right? Fail. So this is gonna fall over now because we have another node, and this is gonna print and always return success and go back, return success, and print this last one here. So this is in between 20 and 70, right? Very good. So let's see what happens. 52. So you see that this is between 20 cents. So this is 52, is greater than 20, and it's less than 70. So it goes here, fail. This is 52, so it prints. This is between 20 and 70, and I'm done comparing because now it returns success and goes here and returns success. But let's go ahead and see if we can actually print something else. 50, 42, 72. You see now 72 is greater than 70. So this return false went here, value comparison. That was true. Log, our log was value greater than 70, and then indeed we have value greater than 70. This returns success, so I'm all set. Return success. I don't fall onto the log because I return success, and log. I'm done comparing. So you see that now here we are on something, right? Because now we have a different logic that it's basically we can implement this logic by adding nodes here. And switch between the nodes with the selector and sequence. And then we have also other interesting things like, for example, a wait block or rather a loop. We can keep adding logic here. So now another thing that you can notice here is that this subtree here is exactly identical to this one here. It's just changing basically this like leaf node values here. So what happens is that you can actually save a subtree, right? Like you can build it, you can model it like using another behavior tree designer, save it, and then plug it in as a call to that subtree under this node here, right? So you see that now you can create more complex, very complex artificial intelligence systems by adding composing basically very complex systems by adding subtrees like this, right? And let's say, for example, right, and we're gonna see this how it works in our system, right? We're gonna connect all the pieces together. That you can use a system like this to basically first optimize our routes, then dispatch them to the fleet, and then start with a block here that is basically a loop block that is going to start monitoring the fleet, right? And it's going to start monitoring the fleet, and it's going to trigger optimization autonomously when there is something wrong with the fleet. For example, a track breakdown or like a delivery is not it doesn't happen within the specified time window and so on, right? So you see that now you can create this artificial intelligence system here for our agent. It can be very, very complex by adding simple subtrees here. And how are we going to do that, like to optimize our fleet? Well, we're going to use whatever the task that we have here, right? So under agent, you see optimize component, and we can select the agent, the component, and the interesting part, of course, is going to be also to write our own leaf tasks, right? But this is all the time I have for this video here. I hope you enjoy. Behavioral trees are very, very powerful, very useful techniques to model very complex artificial intelligence systems with simple blocks and connecting them in this sort of way here. So I hope you enjoyed the video. Next video we're gonna see how we plugging all the pieces together. So how we are going to create the routing agent, set these components, and then create a decision maker and use the behavior tree to optimize our routes. I hope you enjoyed, and I see you in the next video. Thank you.